So let's solve Q1, which says we have this type of circuit where qubit 1 we operate that over qubit 1 as our gate, and then it is followed by a controlled NOT gate. So this is the problem in hand. So it's overall a linear operator, right? Which is operating over a t qubit. So we can write it in a 4 cross 4 unitary matrix form, right? So what would be the corresponding unitary matrix? So this is the question which is asked here. So the logic is that you need to write the t operating over 0 0 in the form of a vector, t operating over 0 1 in the form of a vector, t 1 0 and t 1 1, right? This is what you need to do. So first you need to see what would this circuit do when we apply 0 0, right? Right? What would happen? 0 0 देंगे तो if you input 0 0, the first branch will be plus, which we also write like this, correct? And the second qubit is 0, right? Now it is operated over the, operated by the C0 gate, right? So C0 gate, what is the property of C0 gate? If C0 gate operates over 2 bits, right? X and Y, for example, just so what would happen? This is called controlled qubit. This is called target qubit. So if control qubit is 1, the target qubit gets flipped. So by using this logic, we will get 0 0 because our target is 0 here, so nothing would happen to the control bit is 0, so nothing would happen to control target bit, but this will be the case, right? So if we write in the equivalent vector notation, you need to write like this: 0 0 0 1 1 0 and 1 1, right? So 0 0, the amplitude corresponding to the state 0 0 is 1 by root 2. Please let me know if there is any mistake. 0 0 1 by root 2, right? Similarly, if you go through all the 0 0 0 1 1 0 1 1, we will get the corresponding column. So here this column would become 1 by root 2, 0 0 and 1 by root 2. If you pass 0 1, I think it will be 1 by root 2. Sorry, if you pass 1 by root 2, 0 1. So if you pass 0 1, what would happen? We will get 0 1 plus 1 0, right? 0 1. So 0 1 and 1 0, right? With amplitude 1 by root 2 and 1 by root 2. And when we pass 1 0, then 1 0 will become 0 minus 1 by root 2 here. So we'll have 0 0, right? And we will have minus 1 1, right? Yes. Minus 1 1 by root 2. So t, right? Next, if we pass 1 1, what would happen? This is the 1, right? So we will have 0 1 minus 1 0, right? So this is the corresponding, correct? If we have this one advantage or one utilization is if you have any general qubit now of type A0 0 plus A1 1 and Q1 of type B0 0 plus B1 1, we can easily evaluate its output state, right? What you need to do, you have to multiply this with the A0 B0 right? Let me know if I'm making any mistake. A0, B1, A1, B0, and A1, B1, right? Right? So this will give you the composite output composite state, because you are now observing this as a whole box, which is you call T, right? And the corresponding operator is UT. So this is one thing. The next question we have here is that we are using controlled NOT gate, right? But for the first qubit, we are having any general qubit of type A00 plus A11. So what would happen to this qubit if we apply minus to the second qubit? And then so this is the objective. So once you solve it, you will see we are having A00 minus A11. This is my first qubit. The second qubit is this. Now we jointly pass it through the C0 gate. So of course, you can first write the initial composite state, right? And then apply C0. Or another way is use C0 ka matrix, use it, and then this is up to you. So I'm using the another approach where I will write as a tensor 0 minus A0 by root 2, 1 minus A1 by root 2, 1 0. Please let me know if I'm making any mistake. A1 by root 2 plus ka 1, right?
Yes, sir.
Now you operate C0 over it, right? So C0 is a 2-qubit operator and the principle is same. This is the target qubit and this is the, control qubit, and this is the target qubit. So the answer would be A0 by root 2, 0 minus A0 by root 2, 1 minus A1 by root 2, 1 plus A1 by root 2, 1 0. Right? So this is the output state. Now it was asked that verify that this is equivalent to A0, 0 minus A1, 1 tensor with minus, right? So as many of you have used this, so let's discuss like that only. Tensor of 1 by root 2 get 0 minus get 1, right? And once you solve it, it will be our left hand side, right? It will be our left hand side. So this is how you can prove that our phi 1 is either this, and this is just the another way of representing the whatever we have. This is, so the conclusion is that this type of C0 will provide or introduce a relative phase to the first qubit if the second qubit is minus, right? You can also check what would happen when we have plus. Nothing would happen. You can verify, right? It will not introduce any phase, etc., etc.